Hello. In this video, I'm going to cover an ALEKS topic on calculating the wavelength of a spectral line from an energy diagram. Okay, so in this question, you're given an energy diagram that shows the allowed energy levels of an electron in a certain atom, and we're asked to use that diagram to find the energy of the electron in the ground state, the energy of the electron in the first excited state. We're asked to determine whether a photon will be absorbed or emitted if the electron makes the transition that is shown by the red arrow. And the last step is to calculate the wavelength of the photon that would be absorbed or emitted. Now let's briefly go over the Bohr's model of the hydrogen atom to understand this question and answer these types of questions. So the Bohr's model of the hydrogen atom states that the electrons in atoms are allowed to move in certain orbits around a central nucleus. Here we see the central nucleus, and these circular lines are what we call orbits. And these orbits are where the electrons are allowed to be. So an electron is allowed to be in this orbit or in this orbit and not in the space between these orbits. These orbits have specific energies and are at discrete distances from the nucleus. We call them energy levels or shells and are represented by the letter N. You will later learn that the letter N also corresponds to the principal quantum number. Now, the energy level that is closest to the nucleus has the lowest energy state. So N equals 1, which is the energy level that is closest to the nucleus, has the lowest energy states. And as you go further from the nucleus, energy increases and the value of N increases. So an energy level with N equals 2 has a higher energy state than the energy level of N equals 1. So now the fact that an electron is only allowed to move in a certain orbit, and then these orbits have specific energy, we can now say that the energy of the electron is quantized. This means that the electron must have a certain quantity of energy in order to be in a certain orbit. And this quantity of energy that the electron must have must be equal to the energy of that orbit where the electron is. Now, for an electron to move from a lower energy state into a higher energy state, let's say an electron is moving from N equals 1 to N equals 2 orbit, it means that the electron must now absorb a photon to get the extra energy it needs to jump from the lower energy state to the higher energy state. That photon will have an energy equal to the difference between these two energy levels. Similarly, when an electron transitions from a higher energy state, like for example N equals 3, into a lower energy state that is N equals 2, it will emit a photon to get rid of that excess energy that it has. And the energy of the photon that is emitted would be equal to the difference in energy between these levels. We can see that in the diagram here. When an electron transitions from a higher energy level into a lower energy level, a photon of light would be emitted, right, to get rid of that extra energy that the electron has, and that photon of light will have an energy that is equal to the difference between the two energy levels from which the electron transitions. Okay, basic terminologies here: a ground state and excited state. Ground state is the energy level that has the lowest possible energy. So in this case, N equals 1 is the ground state. Okay, so the lowest energy level is called a ground state. All other states are called excited state. All other states with higher energies are called excited states. And we can see here that there are two different excited states in this example, N equals 2 and N equals 3. All right, now let's go back to the problem and answer the question that we have. All right, so this energy diagram is showing us the allowed energy levels of an electron, and we can see that these energy levels are labeled A, B, and C, different labeling than N equals 1, 2, or 3. And we're asked to determine the energy of the electron in the ground state. Now, as we just said, the ground state is the lowest possible energy state or energy level. So A here is the lowest possible energy level. We can see that corresponds to 400. And the unit of the energy here is zepto, joule. And the question tells you that a zepto means 10 to the power of negative 21. Okay, well, the unit is already in place in the table, so all we have to do is write the energy of the electron in the ground state, which, as we determined from the diagram, is 400 zeptojoule. We're asked then to find the energy of the electron in the first excited state. The question is asking for the first excited state, which is level B, and level B corresponds to 800 zeptojoule in the diagram. Okay, the next question is, if the electron makes the transition shown by the red arrow, which we can see from C to B, will a photon be absorbed or emitted? As we just said, when an electron transitions from a higher energy level into a lower energy level, it emits a photon of light that needs to get rid of that excess energy that it has. So it emits a photon of light, and that photon of light will have an energy equal to the difference in energy between these two levels. So the answer to this question is emitted. We have a photon of light emitted. All right, the last part of the question is you're asked to calculate the wavelengths of the photon that would be absorbed or emitted. So basically the wavelength of the photon that is emitted. Now, to answer this question, and generally the other questions regarding interconversion of frequency and wavelengths, there are three formulas that we use. So I'm going to write the formulas first, and then we'll go from there. Okay, energy of a photon equals the Planck's constant times the frequency. E represents the energy of a photon of light. H is a constant, which is called the Planck's constant, and this is the frequency of the light. The other formula is C, which is the speed of light, equals lambda, which is the wavelength, times the frequency. So this is the speed of light, wavelength, and the frequency. Okay, there's another formula that we also use to solve these type of problems, and this formula is basically derived from these two. So if I take the bottom formula here and rearrange for the frequency, we can say the frequency equals speed of light divided by wavelength, and then I'm going to use that here and replace it in the original formula. So E, which is the energy of a photon, equals the Planck's constant times C, or the speed of light, divided by the wavelength. Okay, so these are the three formulas that we typically use to answer these types of problems. Okay, we're asked to find the wavelengths, and we know that the electron transitioned from energy level C into energy level B, and that the energy of the photon that is emitted when the electron is transitioned equal to the difference in energy between these two levels. So I can determine the energy of the photon emitted by subtracting the energy level of B from the energy level of C. Now, we've already learned that B has an energy level of 800. Now, if we look at the diagram, we'll see that C corresponds to an energy level of 1150. So the energy now of the photon is 1150 minus the 800, which is equal to 350 zeptojoule. Okay, now the question is asking us to calculate the wavelength. So I'm going to take this formula and rearrange it to solve for the wavelength. So the wavelength would be equal to Planck's constant times the speed of light divided by the energy of the photon. All we have to do now is plug these numbers. Let's start by plugging in the Planck's constant. The Planck's constant, you can find that in your book or on ALEKS. Planck's constant equals 6.62607 times 10 to the negative 34 joules times second. This is important because now the unit of Planck's constant is in joule. Okay, then the speed of light, which again, value can be found in ALEKS or in your book. You can write it like this, or you can write it in scientific notation, and the unit of the speed of light is meter per second. And then we're going to divide that by the energy of the photon. Okay, now because your Planck's constant is in the unit of joule, your energy of the photon must also be in the unit of joule. But we have here the energy of the photon in a unit of zeptojoule. Well, the question is telling you that zepto means 10 to the power of negative 21. So we need to convert the zeptojoule into joule by multiplying by 10 times 10 to the negative 21. I'm going to rewrite this nicely. Proper scientific notation, 3.50 times 10 to the power of negative 19 joule. And then we're going to plug this here, times 10 to the negative 19 joule. Okay, we can see that now we can cross out joule with joule, second, and then the unit of the wavelength that we have at the end is in meter. So when we do this math, be sure to include these numbers in parentheses when you do the math. So I'm going to write the value here of the wavelength. N number would be 5.68 times 10 to the negative 7th, and the unit is meter. Well, when we look at the value or the unit in the table, it is a nanometer. So we need to convert the wavelengths from meter into nanometer. And we'll do that by dividing by 10 times 10 to the negative 9th. We know that the nano, the prefix nano, means 10 to the negative 9th. So when you do the conversion, divide by 10 times 10 to the negative 9th, it will be 568 nanometer. And this is the wavelength in nanometer, 568. Okay. There we go. Now we know how to calculate the wavelengths. In some cases, you are given, or in some other types of problems, you are given the wavelengths of the photon of light that is emitted, and you asked to find the energy. In this case, you're typically not given the energy diagram. So in these types of problems, if you're given the wavelength and you're asked to solve for the energy, then we're going to use this formula. Okay, hope that helps. And then in the next video, I'm going to go over another different type of ALEKS problem, which is also related to the Bohr's model of the hydrogen atom.